the talks by Victor, and so thank you very much to attend, and thank you first to Victor to be there. So I leave you. I let you speaking. Can you open your slides?
Yes.
So I should say that this okay. The
Yes.
site is already updated. Okay.
Okay. Yeah. So I am going to be talking about 3 topics, and I'll explain to you why I added an extra topic. So I'm going to be talking about self-normalization, Taylor's law, and copulas. And at the end of the presentation, I will tie them all up. Now, my main reason for including copulas, well, there are 2 big reasons. One of them is that in ecology, there's very little use of copulas. I looked at, I worked in copulas some time ago, and I found that only recently people are beginning to work on copulas. And so I decided that this would be a good opportunity to expose our master's students and other members of EcoDep to the Copula problems, to the Copula approach, and so that, everybody has some idea. Basically, I'll tell you a little bit as to how this wrap up. So copulas is a way of taking independent variables into dependent variables, okay? Transferring dependent into independent. And the Taylor's law that I will present is for independent variables. So this would be one approach of extending it to dependent variables. Now, the self-normalization is a method that is used to prove Taylor's law and to develop a lot of results in martingale theory, which I will discuss. So the 3 themes are highly correlated. And okay, now, okay, so this is the beginning of the presentation. Okay, so I started many years ago doing some climatology, and together with a geophysicist and a student, we obtained a result on detecting shifts in correlation and variable with application to El Nino, Southern Oscillation, monsoon, and rainfall relationships. Now, so as we all know, the correlation coefficient is the most widely used measure of dependence. So we did this several years ago, and it had good acceptance. It has been widely cited. Then another paper that I wrote in oceanography relates to the Indian summer monsoon and El Nino Southern Oscillation. By the way, Mark Kane is the first person that predicted El Nino. So I was very lucky to work with him. Now, in this case, we spoke about another measure of dependence, which is association. So we have the correlation is a measure of dependence, association is another measure of dependence, and it has a theory behind it. Now, I am going to the third way of doing dependence, which is Copula Approach. So this paper with my former student Laurent Colette and one of his colleagues appeared in the Journal of International Banking and Finance, and it has had a wide impact in the banking industry. So it has over 100 citations, and it's going up. It is being used for various things, including gambling, and at any rate, so this is a way of diversifying portfolios so that you are protected using copulas. Typically, the way people diversify their portfolios is by the correlation between the variables, but as you will see, the correlation is not a good measure of the actual link between the assets. Okay, so now, next thing. Why copulas? Well, here is a slide. Let me see. I need to make this a little bit smaller. Well, okay. So here there are two scatter plots. The left scatter plot has what we call a dependent structure, which is Gambo. The right scatter plot has a dependent structure, which is called Gambo. So one is Gaussian, the other one is Gambo. And both of them have identical gamma 3-1 variables. So the marginal distributions are gamma 3-1, and so forth, but they have different dependent structures. What is surprising about this is that they have the same correlation. So the correlation is not really telling you what the dependent structure is. Okay, so that's the message. Correlation is a measure of linear association, but its usefulness is limited to situations where you are looking at how close to a straight line your path is, as opposed to general dependent structures, as I will describe. Of course, correlation has many approaches. You can break things into portions, but now, just to set the notation, I am just going to start with some very basic things. So we have a probability density function f of x, and cumulative distribution functions, which is going to be called capital F of x at x alpha, which is the integral of the density up to alpha. It's the probability that x is less than or equal than x. Now, so you can relate the density to the cumulative distribution function by taking derivatives. Okay, now the inverse distribution function, which we will be needing, is actually, there's a term in banking which is called the value at risk. And when I originally gave this talk was to banking people. So the value at risk is the value x sub alpha, such that the probability that x is less than or equal than x sub alpha is equal to alpha. It's equal to 1 minus alpha, actually. There's a typo. Okay, now, so the inverse function, okay, the value at risk is the inverse function of x at alpha. So it's just to say that when you want to, you can always invert distribution function. If in this talk, we will assume that all distribution functions are continuous, okay, bivariate continuous. Now you can stop me at any time if you have a problem. Then the uniform random variable and its cumulative distribution function is probability that x u less than or equal than little u, which is equal to u. Okay, so that's the uniform random variable. Now, how do we simulate random variables? So again, this is a very basic review, but I understand that some of the people in the audience are students, and there's a very broad scope of background. So now in order to generate variables, what we do is we take a uniform random variable. So let's say that we can generate uniform random variables with a random number generator. Then how do we generate an arbitrary distribution function, continuous? Well, all we need to do is to take the inverse function. Okay, so this is the cumulative distribution function for a random variable x. We take the inverse function at u, which is the uniform random variable, and call that y. That is the variable that we are generating. So we have a lot of values for the uniform, and we are going to plug that into the inverse of x, and that gives us a variable y. The claim is that the distribution the random variable y has the distribution fx. It's an easy thing to see, but you see, you can start with uniform variables, and then from that generate any distribution function that you want. So let's see, the cumulative distribution function of y at x sub alpha is the probability that y less than or equal than x sub alpha, which is equal to the probability that fx inverse of u less than or equal than x sub alpha. Okay. Now tell me if I'm going too slow or too fast, and please stop me at any moment. I'm happy to answer questions, and so feel comfortable.
Everything is fine, I guess.
Are there any questions so far? Okay. So then, so the probability that y less than or equal than x alpha is the probability that f inverse x of u is less than or equal than x sub a. And then we use the fact that the function is continuous increasing. You take the inverse function, so that's the probability that the uniform less than fx of alpha, which is equal to fx of alpha. That means that the cumulative distribution function of the random variable y is fx of alpha. So that's how you can generate, from this method, you can generate any distribution function that you want from a random number generator of uniform variables. Now, this is very important in the context of copulas, as you will see. Okay, so now a key fact is that if we take our distribution function and evaluate it at the random variable associated with the distribution function, so this will be the cumulative distribution function, which is deterministic, evaluated at a random variable, then this is going to be a uniform random variable. So the probability that f sub x at x less than or equal than u, so I'm going to show that it is uniform, that's equal to the probability that x less than or equal than f inverse of x at u, which is equal to fx of x, fx inverse of u, which is equal to u. So what this means is when you evaluate the cumulative distribution function at the random variable that it's associated with, you end up with a uniform distribution. Again, these facts are very important, and that's why I'm reviewing them. Any questions? Okay, so the next thing is to notice that you can do this in copulas. We're going to discuss the bivariate copula, so I might as well write the definition of the joint distribution of two variables, and the copulas will come from this. Okay. Question? Is there any question? I heard somebody talk. Okay. Now let's see. Now, let me ask you a question. Yes, go ahead. I couldn't hear you.
J'ai rajouté un 7e point pour le droit à la déconnexion quand même.
Oh, are you speaking in French or in English? Je peux parler.
Sorry, there is some additional noise. I don't know the origin.
Oh, I see. Okay. Okay, no problem. So then two variables are independent if the joint distribution function factors as the product of the distribution functions. Okay, so that's a known fact. Now, a measure of linear dependence is the Pearson's correlation coefficient. We're going to go beyond this, but let me just review find out what is the problem with the correlation coefficient. Why do we want other measures of dependence? So the correlation coefficient rho has values between -1 and 1. It is a measure of linear association, okay, in that the correlation coefficient of x and y is equal to 1 if y is related to x by a straight line relationship. So when y equal to ax plus b, the correlation coefficient is equal to 1. On the other hand, if that's for a and b, for a positive. If a is negative, the correlation coefficient then becomes -1. And the definition of the correlation coefficient is the expected value of x minus ex times y minus ey over the square root of the variances of x and y. Now, this is a very important fact. If x and y are bivariate normal, then the correlation of x and y is equal to 0, implies that x and y are independent. Now, let me ask you, is the reverse true? So this is a question to see where we stand. If the question is the correlation coefficient equal to 0, will that always imply independence? So that's the question. Yes? If you have two variables which have a 0 correlation, does that mean that they are independent in general?
The answer is not.
And what, can you tell me an example or why not?
An example, I remember, say, like we have x have it could be Gaussian or uniform distribution, and another random variable like z is equal to x multiplied by y.
Okay. Well, I'm sorry, this is not a quiz, and you are giving me a very advanced answer. So
I don't remember an example.
I'm very, very impressed by, you know, and happy that you are participating.
Sorry, Victor, I can give an example to show that the correlation to 0 implied not imply x and y are independent. For example, you can take x is the random uniform on -1, 1.
Mm-hmm.
You will have the x e the x equal to 0 because it's uniform, and you take y is x squared.
Mm-hmm.
So you have x and y are independent, but the correlation is 0 too. So we just have the relations, just they are not correlate. I don't know how to say in English. I'm sorry for my English.
No.
Not correlation, have no correlation, but they are. We cannot say about the independent.
Okay. Okay. Let me give you another example about this. Thank you very much. I appreciate you're very active, and I appreciate that. I really like when that is happening. So, okay. If we go from so here's an example where you can have, suppose that you have a uniform random variable, as someone said, and you take y equal to x squared, uniform between -1 and 1. So this is what the student was telling us. And you let y equal to x squared.
Yes.
Then so that's exactly, I mean, that's the very perfect example you gave me. So if you know x, that completely determines the value of y. If you know the value of x, you know what the value of y. So they are not independent, okay? They are dependent. But if you look at the correlation, you can calculate the correlation. The correlation is, okay, so I guess this is, the correlation is actually 0. They are completely dependent, but the correlation is 0. So this is an example that shows that unless you have bivariate normal or in general elliptical distributions, you will not have this property. So the correlation equal to 0 doesn't mean that the variables are independent. As a matter of fact, they could be deterministically dependent. So that's a very big problem. Now, a lot of money in the billions of dollars have been lost because people do not understand this. Some people, especially in the 80s, where everything related to asset management, the way people divided stocks and tried to diversify by thinking that the assets were independent, was on the basis of taking values of the correlation that were close to 0.
Okay, I'm sorry. Just one thing, I don't see just you have the if xy is bivariate normal. So you have the last point, that the correlation to zeros that not in general implies that x and y are independent. I'm agree with this. I'm so sorry for
you don't agree with this?
Yeah, I don't see the previous point. You say that x and y is bivariate normal. Okay.
Oh, univariate? No. What I said was x is uniform between -1 and 1.
No, I'm just now I agree with you.
Okay, well, thank you.
Sorry for my mistake.
No. I appreciate this because that helps clarify things. I guess there is more than one thing here. The correlation between x and y on here,
yeah,
the relationship between them is deterministic, but they are completely related, but neither the correlation is not 1, even though they are completely related. You can calculate the correlation. And as a matter of fact, the correlation is equal to 0. So, so this shows the two extremes. So if the correlation is 0, that doesn't imply that the variables are independent. You have to think of bivariate normal distributions, or more generally elliptical distributions. Okay, so let's go to the next. Now, as I told you, I wrote this for bankers, so I am giving you examples on banking, but you can think of this as equal. This, as I told you, copulas are just beginning to be used. I'll show you a couple of articles later on that say that it is time for ecology to start using copulas. So if you go to Google and you Google copulas ecology, you can only find 2 or 3 papers. So it's a very good time to learn this. So suppose the probability of default. Suppose that we have V is an asset value and L are liabilities, okay? Then the probability that V is less than or equal than L is the probability of default. So the asset value is less than the liability, so then you default at this case. So probability that you default is probability that V is less than or equal than L. Now, the common assumption is that V and L are independent, okay? However, what about if V and L are driven by a common factor, T? For example, currency or market valuations. So the asset and the liabilities are driven by the value of the currency or the fluctuation of the market. So in this case, it is natural to assume that these two are dependent. Now, the correlation coefficient frequently will not be a good measure of dependence between V of t and L of t. That is the valuation depends on t, on the common factor, and the liability on t. Okay, when these functions are not linear in t. L of t is not linear in t, and V of t is or V of t is not linear in t. Now, so the copulas are used to deal with these situations. So the copula function is a function that captures, in a very general context, all the dependence in a vector of random variables when the marginal distributions are given. So here we have, there's a joint distribution function. Now I'm telling you that there's a function, another function. So you have the joint distribution function. There's a second function that captures all the dependence, okay? The copula is that function. So when you have marginal distributions are given. So this is the brief, the end of the class is just this statement. Copulas are joint distributions of uniform random variables. That's all you need to know. So once you have that in mind, so copulas, they might sound mysterious, but they are just joint distributions of uniform random variables. And we are going to exploit this fact and see this is a very powerful tool, which was actually developed by the insight of a French mathematician called Fréchet. I once was visiting Paris and I sat on Fréchet's desk. So I'm very happy. I looked for some papers, but I couldn't find papers. But at any rate, so Fréchet mentioned to Nelson, who is an American mathematician, about the possibility of doing this, and Nelson developed a theory. So what we are going to see is the theory that Nelson developed, but it was basically the insight of Fréchet. And there's something known as a Fréchet copula. Okay, so as I said, a copula is a joint distribution of uniform variables. So you see, if I have this, is the axis is u. Okay, if this is u and this is v, and I have this pyramid, you have, this is a a joint distribution of U and V determined by this particular surface. Now, so what is associated with every joint distribution? There is a copula. So that's a fact, and I'm going to show you how to find it. But let's see, if I take a joint distribution of uniform variables, then the associated copula is just the same joint distribution, okay? Because, okay, so that's trivial because the probability that U less than or equal than U, V less than or equal than V is C of VU. It is actually a function of uniforms. Okay. 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 So now, given any joint distribution of two variables, there is an associated copula. Now, in this class, we are restricting our attention to continuous variables, and sometimes you have to qualify these statements if you do not have continuous variables. So we are just, to make things as simple as possible, we are assuming that we have continuous variables. Now, so how I claim that for any joint distribution, there is an associated copula. Question is, how can I calculate the copula? Okay, so, and I have divided this into steps. The first step is to find the marginal distributions of X. Okay, so first find the marginal distribution of X and the marginal distribution of Y. So you have a joint distribution, you can find its marginals, then you calculate the inverse transforms. Okay, you take the inverse function, evaluate it at U and V, where U is uniform and V is uniform. Remember, we know how to do that. So if then what I have here is a function, U is between 0 and 1, because f of x is between, the value of f of x takes values, f of x is between 0 and 1. So I have fx inverse of U, where U is between 0 and 1. And what you do is you take your joint distribution and evaluate it at fx inverse of U, fy inverse of V. And that gives you the copula. So if you give me a joint distribution, no matter what joint distribution you pick, under regularity conditions, then I can give you the copula. All I need to do is I take the inverse function of x, the inverse CDF of x at U, the inverse CDS of x at Y, at V, and then evaluate it at the joint distribution of x and y. That's the copula. It's a uniform. It's a joint distribution of uniform variables because okay, so because U and V are between 0 and 1. Okay, so let's check that that is indeed a copula. So we have f sub x, x, y of fx inverse of U, fy inverse of V. I can then take this, this is the probability that x is less than or equal than fx inverse of U and y less than or equal than fy inverse of V. Then I can take the inverses to the other side and I get the probability that fx of x is less than U and fy of y is less than V. But you remember that we said that we showed that if I take a random variable, if I take a distribution function and evaluate it to its associated variable, that's uniform. So this is a joint distribution of uniform variables. So that's the proof. Is there any question about this? So that's how you can find copulas, the copula for a joint distribution function. Now, those of you who might have studied actuarial science or might be interested in insurance probably know a lot about this, because you know, this theory, the book of Nelson was published in 1959, but the theory took time to develop, and it was only in the, I would say, the 80s when things began to take off. And this was because actuaries realized that that this was a very useful tool. You see, they had, for example, they wanted to give value to a catastrophic event. For example, if you have an earthquake, you have a joint distribution of earthquake and the impact of the earthquake and the cost of the fire. So what is the cost of an earthquake together with the cost of a fire? So you need a joint distribution for that. And they found that when they went from region to region, the relationship, the relationship between earthquake and fire or other two variables was the same, the dependence. But the marginals could be different. For example, you have an earthquake in Indonesia and a fire. Well, this is perhaps not a very exact example, but it gives you a sense. Suppose that you have two cities in different countries with the same properties. The buildings are the same, roughly speaking, built. And so if you have an earthquake, there will be a damage, okay? So this damage in one country is in rupees. And then the damage in another country could be in dollars or in euros, okay? Now, euros, so the marginal distribution for the damage is either in euros or is in rupees. And you want to put them together. You see, they knew that they know that the joint distribution, that the dependence between the damage of the earthquake and the damage of the fire was the same, but they have different currencies. So they wanted to join their knowledge of the dependence to the marginals. Okay, so thanks to actuaries, we have a lot of theory of copulas developed. Okay, that's a little bit of history. Now, so, okay, now properties of copulas. So copulas construction does not constrain the choice of marginal distributions. And it provides a way of obtaining joint distributions. Okay, as I mentioned, Sklar, motivated by a comment of Frechet, showed that joint distribution functions can be written in terms of a copula if the marginals are continuous, and there is only, if the marginals are continuous, there is only one way of doing this, okay? So if the marginals are continuous, there's only one way of getting a copula. Now, if I have marginals, so now let's say I have different currencies, or, you know, okay, so here's the next level of abstraction. Suppose that I have a copula, that means a dependence function. So it is intrinsic to the dependence of the processes. And I want to attach to it marginal distributions, like the distribution of rupees against the distribution under euros. Then what we have is you can find for that copula, you can find the joint distribution associated to that copula and those marginals. And that is the vector fx inverse of u, fy inverse of v. Okay, so you take the copula C of fx inverse of u, fy inverse of v, and that gives you the distribution that you're looking for with the appropriate marginals. Okay, so that's how you take a copula, and that's how you can associate with the marginals. Now, if you take y equal to g of x, where g is strictly decreasing, a decreasing function, then the copula is able to capture the relationship between x and y. More precisely, the copula of x and y is the minimum of x comma y. If it is strictly increasing, it's the maximum. So the copula in this case is fully determined if you have strictly increasing or strictly decreasing functions. Relationship is strictly decreasing and decreasing. Okay, now out of this lecture, the next item 6 is the most important. This is the most important of this lecture. So in that it shows to what extent the copula is a foundational concept in probability. So there is this there's this expression: any joint distribution function under the conditions we have stated can be written is actually the product of the marginal distribution functions times the partial derivatives of the copula associated with the density at fx of x, fy of y. Now, okay, so I tell you, this is the most important thing. I work in an area called decoupling. So I want to pretend, I want to find situations under which variables are independent. So here's a quiz. For what C12, what fraction C12 will give me independent variables? How do you know? So in this expression I have, if I have C12 to be what, these two variables x and y are independent. There's one answer only. Is the question clear? I guess it is not clear. So how can I put it? Okay, so I guess I'll give you the answer. If C12, which is the partial derivatives of the copula, associated with the joint vector, if C12 is equal to 1, then the joint distribution of x and y, the joint density, is the product of the marginals, right? Correct? Raise your hand if yes. I guess I lost all my audience. Let me see. No, I have 13 participants. Okay. Anyways, so let me think. So I hope that this is clear. So you can always, so the difference between dependence and the independence is the copula function. Once you pick a copula function, you can get back your density function. Now, Schwarzer and Wolf showed that copulas capture all the dependence contained in the joint distribution of x and y, in the sense that for any strictly increasing function, the copula associated to g of x, h of y is the same as the copula for x and y. So if you take increasing transformations, the copula doesn't change. Okay, now it's 10:49. Maybe it's time to take a break. So I propose a 10-minute break, and we will continue with this. Is that okay?
Yes.
Okay, so we'll be back in 10 minutes. Okay, so while we wait, I'm trying to connect some papers on the papers on copulas and ecology.
So let's go back. Let's go. Shall we go back to? So I should say that the text of Victor text is online, and in fact there are 3 texts that you will find online, and also maybe people may be interested I don't know if you hear me. Maybe you didn't hear me. I'm sorry. I want to say that the texts are all online already.
Okay, thank you. Okay, so let's see. So I'm trying to connect to my iPad. Let's see if I can. Okay, good. So, okay. So what I have here is I was able to get the papers. So I'm just going to put them online. So this paper is from 2019. So it shows a path for multivariate analysis of ecological communities using Copulas. So I guess it would be important to keep a list of papers published in ecology and Copulas, using Copulas to get a broad sense. And this is in some sense a nascent field. Now, let me see, I think I have another one. So there is a paper on, so this is in the journal Statistics in Ecology. No. Let me think. Let me see if I can bring it down. Okay, so, okay, Advances in Ecological Research. And the name of the paper is Copulas and Their Potential for Ecology. And this paper was published just in 2020. So you see, this is a very, I think, important paper for our project, if you're interested in copulas and ecology, because they, here they are providing you some ideas as to where you might apply it. Now, these papers have been posted online at the website. Is that correct, Paul?
Sorry, everything is online. You have you may see that on the bibliography things. Okay.
Okay, so it's in the bibliography of online. So,
if anyone needs it, I will just send him. Okay.
Okay. So let me see. Okay, so now let's see. So I will stop this share and I will go back to where we were. Okay, so I guess 10 minutes is up. Let's see. Let me see one thing.
I'm sorry, but
yes.
okay.
So I am back. Yeah, that was 10 minutes. So unfortunately, I got out of the process and I had to reload the slides. So let me just go fast through them. So to recap, what we have is Copula is a way of dealing with dependence. And for every joint distribution, there is an associated copula. And every copula can be used to produce different joint distribution functions. So if you have marginals, for given marginals, you can construct an infinite number of joint distributions with those marginals by following the recipe that I gave you. And so now, let me see. Okay, Sklar. So again, I said that this was the most important property. If you know measure theory, you would see that the copula, the copula density evaluated at these values is nothing else but the Radon-Nikodym derivative of the joint density divided by the product of the marginals. So there's a connection between this and measure theory, and this identity can be used to produce decoupling inequalities. I might be able to show you that at some point, where you can take dependent variables, connect them to information measures, and then get, as a result, an inequality for a sum of dependent variables, like a probability that the function of a sum of dependent variables is less than the measure of entropy, plus the probability that the same function of independent variables with the same marginals is bigger than x. So you can use this to decouple dependencies. Now let me see. Okay, so I guess this is where we were. So copulas extract the way in which the variables move together, no matter what scale is used to measure them. Okay, so now what are the drawbacks? Copulas are not the panacea for everything. They are good, but one has to be able when one uses them. Copulas are whole functions. It's not a single number like the correlation. So it's in that sense, it's a disadvantage because you need to know the entire function to be able to check whether or not there is dependence. However, there are ways in which you can synthesize things, and I'll explain how. So one needs to identify the appropriate copula, and this can be hard. Actuarial scientists have a big library of copulas available, and they have copulas for earthquakes and fires, copulas for various different events, joint asset or joint losses. And so one can look at that library and then see if the scatter plot is adjusted well to the function, to which copula. So the calculations required are frequently linked to a particular copula. The correlation coefficient cannot be calculated using only the information provided by the copula. So if you just know the copula, you cannot tell what the correlation is. You need the marginals, and that's natural. So in the following transparencies, I will deal with the methods of dealing with these problems that I presented here, including a method for generating copulas, several examples of copulas, and 2 new correlation coefficients that can be computed solely on the information contained in the copula. Let me think. Okay. So if I want to construct a joint distribution, so suppose I want to construct a joint distribution. There is a library, an infinite number of possible dependence functions or copulas. These are the joint distributions of uniforms. So if I want to construct, there's associated with that, there's an infinite number of distribution functions. So because you have many marginals. So the way to construct a joint distribution from a copula, so you have the dependence function and you evaluate the copula at the cumulative distribution function of x at x, cumulative distribution function of y at y. So this is the way to obtain or construct a joint distribution based on a copula. So the way you can work is you look at the copulas that are available in the library, or you try to adjust, you find which copula is most appropriate, and then you can attach to it whichever marginals you might want. So you can go from putting marginals normal, putting marginals t, so in that sense, this is provides a lot of flexibility. When we think about statistics, typically we think of a fixed number of distributions, the classical distributions, normal, bivariate normal, bivariate t, and so forth. And typically those come with fixed marginals. Here, what we're expanding the scope of statistics and say you are able to take the dependence function separate from the marginals. So you can, for example, take a Gaussian copula. So there's a copula that is called a Gaussian copula, and give it marginals, let's say exponential. This will give you a new distribution that has the dependence function of the normal, but the marginals are exponential. If you take a Gaussian copula and you put Gaussian marginals, then you get the normal distribution. But this allows you to construct, to have a very versatile way of constructing distributions. And many in the 80s, and I don't know to what extent now, one way of you to become famous was to find a new copula that was useful. So there are copulas named after a lot of people. It was a high day. Unfortunately, I didn't manage to name any, but oh well. But who knows, maybe you can find one. Okay, so now let me see. Okay, so now let's see. So in order to construct a copula with particular marginals, so what you do is the following. So you want a copula with particular marginals, we could do the following. We pick the marginal distributions for our problem. In the case of asset values V and liabilities L, it would be FV of V and FL of L. Step 2, pick a particular dependent structure from a library of joined bivariate uniform variables. That's the copula. Step 3, evaluate the copula at the distribution function, at the marginals that you have. This gives you a distribution function, FVL, which has the marginals FV and FL. Now, if you want the best introduction that I know, as an article of copulas is a paper by Valdez and Fries, which you can download from the web. You just type their names and you can get it. I'll pass it on to Paul. But that's an excellent introduction to copulas. And moreover, you don't have to buy a book. Of course, there are a lot of books on copulas these days, but that's a good introduction. Now, I'm going to now give you examples of copulas. Okay, if X and Y are independent, the copula associated with those variables is just U times V. That's the copula of independence. Then the Gaussian copula. So what you do is you take the joint distribution function of X and Y, which is a bivariate standard normal, and then you evaluate it at the marginal of X. This is the CDF of X, the probability that the normal X is less than or equal to capital X. So it's like, this is the CDF of the normal evaluated at X. And this is the CDF of the normal evaluated at Y. So this is basically you have the joint distribution function of the normal evaluated at the inverse distribution functions of the marginal. Okay, so that's the Gaussian copula.
I didn't get that. Could you try again?
I'm sorry about that. That was Siri. I have another machine working. Okay, I just killed Siri. Okay, not really. I just closed the machine. Okay, so now is it clear what the Gaussian copula is? If there's any question, please let me know. A very popular way of constructing copulas is called the Archimedian Copula. And so we take psi to be a function from 0, 1 to 0, infinity, such that psi is convex and strictly decreasing, and psi of 1 is equal to 0. Okay, so this is the picture. Then the copula of U and V is going to be the inverse of psi evaluated at psi of U plus psi of V. This is a copula. And there are multiple, when you replace the function psi, you get a different copula. So for example, this is from the book of Nelson, 1999. So in this case, you have, if you pick the function phi to be 1 over theta, t to the minus theta minus 1, this satisfies the properties that we stated here. It's decreasing and it's 0 at 1. Okay. So it's 1, when t is equal to 1, this is equal to 1. And then minus 1, that's 0. Okay, so this is the appropriate generator. And the copula is the maximum between U inverse at the U at the minus theta plus V at the minus theta minus 1 to the 1 minus 1 over theta and 0. That's the copula. Then you can also take a generating function as 1 minus t to the theta, and you can get from there a copula. And each one of these has a name. We will see names later on, but anyways, as you see, there's a multitude of possible dependencies that you can treat. Now, theta is usually estimated by using the Spearman's rho and Kendall's tau, okay? So now let's continue. So those are examples of copulas. Now, from my paper, the paper that I presented before, so I'm going to show you copulas with their names. So there's the normal copula or the Gaussian copula, and this is how you obtain it. Joint distribution of normals evaluated at the inverse of the marginals. The parameter range is rho between -1 and 1, okay? Because this depends, the joint distribution of the Gaussians depends on rho. And complete dependence is when rho is equal to 1 or rho is equal to -1, and independence is when rho is equal to 0. So this copula is parameterized by rho, which is between -1 and 1. Then another very important copula is the student copula, which is obtained by taking the joint distribution of the bivariate t evaluated at the inverse of the marginals. And again, that the copula of independence, if you want to check for independence, the parameter should be close to 0. Then there's the Gamble copula. So Gamble got his name associated to a copula. And this is one of the copulas that I showed you can be generated from decreasing functions. And it comes with a parameter beta. And complete dependence is when beta is equal to 0. And complete and independence is when beta is equal to 1. Then there's the rotated Gamble again, and the Gamble, there's Gamble, rotated Gamble, Clayton copula, rotated Clayton. Okay. So the measures of dependence using copulas. So the appropriate measures of dependence are, it's typically Spearman's rho or Kendall's tau. So what is Spearman's rho? Is the expected value, is 12 times the expected value of the cumulative distribution function of x at x minus 1/2, the cumulative distribution function of y at y minus 1/2. So that's rho of xy, and it can be written as 12 times the copula of uv minus the product of u times p du dv. So you see, the Spearman correlation is basically the distance between of the Spearman correlation between a joint distribution is basically the copula associated with that joint distribution, the distance of that copula minus the copula of independence. Very interesting. So the Spearman correlation is measuring the distance between the copula to the copula of independence. Kendall's coefficient, can be written also in terms of copulas to be rho k of xy equal to 4, integral from 0 to 1, integral from 0 to 1, c of uv, d c uv minus 1. So again, this the Kendall's tau, or the Kendall's correlation, can be computed entirely from the copula. So it doesn't depend on the marginals. Both Kendall's and Spearman's are both depending on the copula only and not on the marginals. Now, so let's just review the properties of those coefficients. So both Kendall's and Rho's correlations are 1 when y equal to g of x for a strictly increasing function. Okay. In this case, I say y equal to x squared, but this is for x positive. And rho s and rho k equal to -1 whenever y is equal to h of x for a strictly decreasing function. So, okay, so if they are deterministically related by an increasing or a decreasing function, the correlations, these correlations are either 1 or -1. Now, for arbitrarily strictly increasing functions, the Spearman correlation of xy is the same as the Spearman correlation of this increasing function of x and increasing function of y. The Kendall's correlation is also going to be the same. So the correlations don't change even if you translate your variables by increasing transformations. Now, so let's see. So here's a little more information. So we have what I wanted to show here is, okay. So this is the relationship between the copulas and Kendall's tau. So when you have a Gaussian copula, Kendall's tau is 2 over pi arcsine of rho. Remember, the Gaussian copula is parameterized by rho. If you have a student T copula, then Kendall's tau is 2 over pi arcsine of rho. So you see, you can then adjust, you can do goodness of fit for your copula based on the value of Kendall's tau. And so forth. So if you, so the idea is as follows. Conceptually, what this is what we do. We have a scatter plot. From that scatter plot, we have a joint distribution that is inferred from a scatter plot. We look at the copula that is related to that scatter plot. Now, let's say that the scatter plot looks like a Gaussian copula. Okay, the copula associated with that is Gaussian. Question is, what type of Gaussian is it? Well, that will depend on rho. Okay, so different rhos gives you different levels of dependence. And if rho is equal to 0, the dependence is Okay, it's independence. Okay. Okay, so now I'm just showing you again the paper that I wrote. Just for banking and finance. This is just the heading. Now, what we did is we studied the movement of assets, the movement of asset diversification opportunities available in international stock markets. So we were looking at for opportunities for diversification. And we did this with correlations and with copulas. Okay, so now this is important because of all the financial crises. You want to be able to diversify your portfolio. And with increasingly globalized markets and contagion, you want to have as diversified as portfolio as possible. Okay. And we studied Europe, Asia, and the United States, and came up with which countries are more closely linked and how can you diversify your portfolio on the basis of the studies that we did. And this is what we these are the data, so the French mark, Japan, this is France and Japan and US. This is the left tail dependence, right tail dependence, which tells us how when there are extremes, how the dependence looks. Now, how do I estimate a copula? So here we have maximum likelihood. Okay, so if we want to fit a copula, okay, so what we do is the following. So how do you do maximum likelihood with copulas? Well, you write your marginal distribution as can always be written as the joint distribution as the product of the marginals times the copula, the copula density evaluated as fx xy. Then you take a sequence of x sub I, yi, this should be a y, independent realizations of the vector xy with copula C, and then you take the log of the joint density times the copula. So what you do is, you see this log, this function, the C1, this separates into two parts, is the log of f of x, plus the log of f of y, 3 parts, plus the log of the C12. So you can get a maximum likelihood estimator that will depend on the parameter of the copula by maximizing, by finding the value of the parameter that maximizes this. Another techniques that we use to assess the fitness of copulas is by using the AIC and the Akaike criteria and the BIC. Okay, then, so we compare dependent structures using likelihood methods. And here, we have the normal versus Clayton copula. And this is what we got. So these are all tables that related to our study, but this is not a course on finance, so I'm not going to dwell into this. So then, so let me think. So we have 10, 11:30. Okay. I think, let me just wrap up Copulas by saying that, well, there's a paper that characterizes joint distributions and Copulas. Basically, this paper tells you how every copula has to look like. So if you have a copula, it has to be of this form. And once you know the form, then you can get you can get certain dependent structures. So if you want to have stationarity, the copula has to have a certain property and so forth. Now, I'm not going to go into this, but the point is that every copula can be written as a function of a sum of U statistics. And this is a very powerful technique that allows you to decouple arbitrary distributions by using information theory. You can look at that in the paper. And so this paper also allows you, if you have a bivariate copula, it tells you how to construct a multivariate copula based on the formula for the bivariate. So you can, you see, you can get strictly stationary vectors. A sequence of variables is strictly stationary if xj1 up to xjk has the same distribution as xj1 plus h up to xjk plus h. And because of the characterization, you will have a sequence of random variables is strictly stationary if and only if the functions g sub I1 up to g sub ic satisfy this property. Okay, so if you want to construct a sequence which is stationary, it has to have, you have to check, you have to create the g's with this property. Okay, so these are just different dependent structures that you can construct using the characterization in our paper. You can construct exchangeable variables, a joint distribution of exchangeable variables. The copula will have to have g's of this type. M dependence, the copula has to have a certain form. Now, there has been a lot of activity in copula, the development of copulas. One of my co-authors, Rustam, who was co-author on the previous paper, wrote a paper on characterization for higher order Markov processes using copulas. There's copula-based models for financial time series by Patton, Andrew Patton. So here is a possibility of developing a time, so a time series approach using copulas has been developed. This is interesting to compare it to other approaches of dependence. Let me see. Okay. So the last thing is there's a lot of talk about reproducibility of experiments. And in this paper, they use copulas, a Gaussian copula, to develop that theory. Okay, so are there any questions about copulas? I guess this is the end of my introduction to copulas. Are there any questions?
May I ask what kind of real application you have in ecology? Because definitely those are quite classical facts, and I wonder about it.
Okay, so what real applications of copulas? Or I did not understand the question.
In fact, I didn't catch the reason why about speaking of copula in these lectures, which are more addressed to ecology questions.
Oh, yes, I should have spent more time on the. So let me go back to the papers. Remember, I sent 2 papers to you on the fact that, so why did I introduce copulas? And how does this relate to ecology? Well, there is not much work that has been done in ecology using copulas, okay? Now, copulas took over the financial world. They took over many fields, including, sociology. You can find a Copula approach to time series, a Copula approach to this and that, and to various fields. But they haven't been used in ecology that much. So this is an approach to dependence. And the 2 papers that I sent you are like the beginning of applying copulas to ecology.
Because in a sense, what I imagine is that copula is very good to model the dependence in a couple or in a finite dimensional vector, but I don't see how it may be used really for time series, because you will lose the the long time dependence, and so
yeah, well,
exactly what is required usually when you work with time series.
So that's what I'm not familiar with the applications of copulas to time series, but there are copula models.
Yes, I understand, because that's a classical transform for sure. For the yes, it was Rees-Clark theorem, and before him there were very many probabilistics which were working with that a long time ago.
Yeah, well,
you have citation to Fermanian, and I even wrote a paper on this, but I was never very convinced about the practical applications.
Oh, okay. So
could I ask, Victor, could I ask you a much more elementary question?
Yes.
Could you please define left tail dependence and right tail dependence? You went over that slide very quickly, and I don't think you actually defined what is the meaning of the numbers in that table.
Okay, so let's go back.
I'm sorry, it's an elementary question, but this is for master students.
No, there's a reason why I went fast. But let me see.
It's a very elementary question, but I don't know the answer.
You don't have to say that. It's I have to find the slide.
Yeah.
Because the slide tells you what the definition is. So okay.
It's on slide 27, Victor.
Oh, yeah, I don't. Oh, 27. Okay, good. Okay, good. So this is the left tail dependence. So it's the probability that the joint distribution function of x at x is less than u, given that the joint distribution function of y is less than or equal than u. Okay. So what you have is, and then the left tail dependence is the limit as u tends to 0. The right tail dependence would be the reverse. So the question is, you see, when you are looking, if you have a joint distribution function.
Excuse me, I still don't understand. In the expression for d of u, there is no lambda. You have limit as lambda goes to 0. Where's the lambda in the expression for d of u?
It should be the limit as u tends to 0.
Oh, that makes a difference. Sorry.
Yeah. Sorry.
Okay.
So it's the limit as u tends to 0. Lambda
Okay,
is
the definition there doesn't make any sense. Now I understand. Thank you. Okay.
Oh, okay. I am so sorry. I didn't go to it and I should have.
Okay, now I understand. Thank you very much.
Okay, thank you. Yes. Now, I guess in talking about what Paul says,
yeah.
So, I want to warn people about copulas. At the same time, I'm an enthusiastic person on them. So I think this is an important topic that Paul has brought in. So we were able to use copulas to study the co-movement of financial markets, okay, and the diversification. And this is a fact that has been proved empirically. So these copulas are useful for finance. Now, there's a story that you will probably find interesting, and it speaks to what Paul said. You know, the collapse of Wall Street. So there used to be CDOs. So they, the debts of housing, the housing market collapse. So in the 80s, the people had many bad debts, and they hid them by creating baskets of debts. Now, let me try to explain what this means. So there are loans, and there are loans, let's say, that are grade 1, grade 2, grade 3, up to grade 5. So in order to sell the worst loans, people created a basket that included some good loans and some bad loans. And so this is basket 1, basket 2, basket 3. And then they joined them by a Gaussian copula. And this is the way in which these financial instruments were created. So the Gaussian copula took over the financial markets in the 80s, and there was an earthquake in the financial world. You remember the terrible collapse of the financial markets? There was a person who I know personally. His name is Lee. His last name is Lee. Now, he came up with the method of joining different debts, as I told you, into baskets, by joining them using a Gaussian copula. And there was an article in the Financial Times about the formula that killed Wall Street. Okay, so this is talking to Paul's issue. So when not used appropriately, copulas can create a lot of damage. So the assumptions that Lee had requested for the use of his approach was that the variables, the marginals, were heavy-tailed, but people in Wall Street were just taking light-tailed marginals. Yeah, just the Gaussian distribution. And so bivariate Gaussian. And so when the extremes, this is related to left extreme tail and right extreme tail, when there was a co-movement, okay, since the tails did not really have any connection, actually, well, no. Because of the way the misuse of the copulas, the entire market collapsed. Not only because of that, but this is related to the Black-Scholes formula. So in the sense that, so when the Black-Scholes formula came up, it became a craze in the stock market. So everybody started valuating financial assets using the Black-Scholes formula. And to the point that it was a self-fulfilling prophecy. So things were following the Black-Scholes formula because of the formula that had been given to do the valuation. In the same way, people were using Gaussian copulas, and everybody was using Gaussian copulas, and they were blind to the reality. So all these statistical methods, okay, all statistical methods have to be done with care. So all of statistics has to be approached with care. But one cannot say that time series or survival analysis in general are not important or should not be studied. One should study them with care and apply them, checking the conditions. So copulas have a vast array of applications in many fields, and as long as you approach it with care, it's applied probability. You're trying to model the world, okay, the reality, and you will try to approximate reality as much as possible. And so if you check your conditions, you will have one way of looking at things or another way. I don't know if that explains, if that answers Paul's question or remark.
Thank you.
Any other questions? Okay, so we still have time. So now I can go to self-normalization if there are no further questions. Okay. Now, I hope that the introduction was at the master's level. And that was one of my main reasons for providing this, because I don't know if there are courses that teach this at the master's level. Let me see, 1 second. Okay, so now we are going to the presentation on okay, so now this is self-normalization. Now there's a quiz here. So this phrase was given by I learned this from a famous probabilist called Jo Dube, who basically was the one who inspired me into getting into self-normalization. And the phrase is, behind every limit theorem, there is an inequality. So what we're going to do next is we're going to learn about inequalities, and that can be used for limit theorems. So this phrase, can somebody suggest who might have said this phrase? Okay, so nonetheless, it was Kolmogorov. So Kolmogorov said, behind every limit theorem, there's an inequality. So this is one reason why I study inequalities. So some people study limit theorems, other people study inequalities, but they are connected. Now, just for a little relaxation, I have the picture of Kolmogorov. Okay, so now let me justify the use of inequalities to do limit theorems. Okay, so suppose that we have a sequence Sn over An, a sequence of real random variables. Then to show that Sn over An converges to nu in probability, Markov's inequality is often used. So you have probability that Sn over An minus nu bigger than epsilon, less than or equal than the expected value of Sn over An minus nu to the p over epsilon to the p. So that's just Markov's inequality. And so if we have a sequence of IID variables, Sn is the sum, then the weak law of large numbers for sums of IID random variables with finite variance uses the case p equal to 2. Okay, so that's how you can get p equal to 2, An equal to n. When the variance is equal to 1. Now, what happens when the variance is infinite? So what type of result can you obtain? So what we want, if we want to prove a limit theorem for situations where the variance is infinite, we will need to deal with the case, where this expectation might be infinite. What about in the case where the variables, where An is a function of the variables, A1 up to x1 up to xn? So in that case, also the classical theory it's not fully developed yet. And so that's self-normalization. You take a sum divided by a function of the same variables. So that's what we call self-normalized. Now, where did self-normalization come from? So these are frequently processes that are frequently found in statistical applications. They have the property of being unit-free and frequently eliminate or weaken moment assumptions. Okay. Now, the prototypical example of a self-normalized random process is the student's t-statistic, which replaces the population standard deviation by the standard, by using the sample standard deviation. So you see, this is the z statistic. If you have x sub I, IID, mean, nu, and variance sigma variables, variance sigma squared, this has a normal distribution. What student did was found the distribution of the situation where you replace sigma by the sample variance. So question is, so the theory, I consider this as the first result on self-normalization, at least that I'm aware of. Now, the question is, what happens when the variables are not normal? What can you say about this random variable when you divide by the sample variance? What happens when they are not independent? Okay, what happens when they have infinite mean? So in a more general context, a standard self-normalized process can take on the form AN over BN or AT over BT in continuous time, where BT is a random variable that is frequently used to estimate the dispersion measure of the process. Okay. So now there are examples of self-normalization. So this is the outline of the talk. So we have examples of self-normalization. We have an introduction and motivation, martingales, MLEs, autoregressive processes, martingales and super martingales. Then we have pseudo-maximization. So the key to the development of the martingale theory of self-normalization is based on the technique called pseudo-maximization, or the method of mixtures, and we're going to go over that. We're going to get exponential inequalities, boundary crossing, and the LIL of self-normalized random variables. Analogous to the Kolmogorov law of the large LIL, this one is self-normalized. So let's see. So the setup is, as we started before, we have IID normal with mean nu and variance sigma square. X bar is the sum of x sub I over n, and Sn square is the sample variance. We have Tn is equal to x bar n minus nu over Sn over root n, which is a t-distributed. And we let yi to be xi minus nu. An is the sum of the yi's. Bn squared is the sum of the yi squared. Then we have that Tn is equal to An over Bn divided by n minus An over Bn squared divided by n minus 1. So you can study the t statistic by using ratios of this type, sum of yi over the sum of yi squared. And that's sort of the type of ratio for which a lot of the theory has been developed. The theory of self-normalization, aside from students' paper, there's some work of Larry Shep and Mallows in the 70s. There's some work of Efron, where he showed the robustness of the t-statistics. Then I guess there will be more information on these things. Okay, so so in 1997, Ginet, Gotze, and Mason obtained a Berriasin bound for the student t-statistic. So this is relatively recent, 20 years. Now, Ginet, Gotze, and Mason proved that the student t-statistic has a limiting standard normal distribution if and only if x1 is in the domain of attraction of the normal law, by making use of exponential and LP bounds for the self-normalized sums. Okay. So this paper is a landmark paper in self-normalization. And some of the key ideas related to, okay, so what is the connection between self-normalization and Taylor's law? So I haven't spoken about Taylor's law, but I'm going to, this is a preview of what will happen next time. So self-normalization, I said, was taking the sum of yi's over the square root of the sum of yi squared. Now, what about the flip side? Suppose that I square both sides. So what about the sum of the yi squared over the square of the sum of yi's? So if I flip this, basically you get Taylor's law. So Taylor's law can be viewed as a self-normalized process, and similar techniques to the ones that are developed in this paper are then used to develop theory for Taylor's law. Okay. Now, for those of you who know large deviations, there's a very important paper of Kim and Chow in 1997. So large deviations typically assume that you know the moment generating function, that you have a bound on the moment generating function, expected e to the tx for your random variables. Well, he was able, by self-normalizing, like I explained before, he was able to prove a large deviation result without any moment conditions. So this is important because who can really check whether the moments are one thing or another? Assumptions are usually something that needs to be checked, but the less assumptions we make, the better off we are. So if you are interested in large deviations, this is an important paper. Okay, so there's a book. If you want to get a perspective of the theory up to 2009, there's a book with Lai and Chow by Springer, which is called Self-Normalized Processes, Limit Theorems, and Statistical Applications. Okay, so now let me start with an example. So we have an autoregressive process. Here we have an autoregressive process, yi equal to alpha yi minus 1 epsilon I. I'm going to connect this to a martingale, okay? So I want to get information about alpha using self-normalization. So in this case, I hope everybody knows what a martingale is. And so you have a sequence of increasing sequence of sigma field. Mn is the sum of the di's adapted to Fn. Expected of dn given Fn minus 1 is equal to 0. And the expected value of dn in absolute value is finite. Okay, so we have the linear regression model when alpha is different than 0. And but it's unknown. We take a sequence epsilon sub I in independent standard normal random variables. We will show that the maximum likelihood estimator of alpha is a self-normalized process. The maximum likelihood estimator of alpha can be obtained by taking the derivative of the likelihood function. And this is the likelihood function. So this is actually the log likelihood function, which when you rewrite it, because we have Gaussians, it becomes this. So this is the log likelihood function, the sum of yi minus alpha, yj minus alpha, yj minus 1 square over 2 minus n log 2 pi. So when we take the derivative with respect to alpha, and if we equate to 0, we can solve for alpha hat. The estimator of alpha is the sum of yj minus 1 yj plus the sum of yj minus 1 square. So now using the definition of yj, we obtain alpha n hat is the sum of yj minus 1 alpha yj minus 1 plus epsilon j over the sum of yj minus 1 square, which can be written by taking alpha outside as the sum of yj minus 1 epsilon j plus the sum of yj minus 1 square. So therefore, in testing a hypothesis about alpha, we can use self-normalized random variables, okay? Now, so if we get inequalities for this variable, then we can get limit theorems for alpha n. Now, of course, there's a very long history of autoregressive processes, and this is not supposed to supersede that. It's just an example. Okay, so what we have now is we let an to be the sum of ym minus 1 epsilon j, and fn is the sigma field generated by the y's and the epsilons. If we set dj equal to yj minus 1 epsilon j, and we let bn square to be the sum of the expected value of yj minus 1 epsilon j square given fn minus 1, that's the sum of the yj squares, yj minus 1 square. Then alpha n hat minus alpha is equal to an over bn square by the formula. So an is just the sum of the yi's, and bn squared is the sum of the yi minus 1 squared. So we are self-normalizing by this quantity, which is the conditional variance. Now, this is the most important assumption. Expected e to the lambda summation of yj minus 1 epsilon j minus lambda squared summation of yj minus 1 square over 2 is less than or equal than 1. And this random variable is an example of an exponential super martingale. This is for all lambda between minus infinity and plus infinity. It provides a good example of a random variable satisfying the canonical condition that we're going to be used repeatedly. So we have an example of a random variable of a process that satisfies a canonical assumption, which is the expected value of Tn is less than or equal than 1, because this is a super martingale. And so the canonical assumption, here we're going to play with A's and B's. And so we take arbitrarily dependent variables, A and B, and we assume that this holds. For all lambda between minus infinity and plus infinity, this is less than or equal than 1. Okay? So this is the only assumption that we make. Under this assumption, one can prove that the probability of A over B squared bigger than X and 1 minus B squared less than Y is less than or equal than e to the minus X squared over 2Y. I will prove other inequalities, but this is an inequality that follows by using Markov's inequality and a few other tricks. I'm not going to prove it here, but anyways, please believe me that this is true. So here we are self-normalizing A by its conditional variance. In the case of the autoregressive process. Now we can apply this bound, the bound on an and minus an, to obtain probability that alpha n hat minus alpha in absolute value is bigger than X, and sum of yj minus 1 square bigger than C is less than or equal than e to the minus X squared Z squared over 2. So what we have here, this inequality gives us a sense as to how far our estimator is from the true parameter when the data exceeds a certain level. So you can use this for testing hypotheses. And if you know that the sum of the yj's is large, you have a sub-Gaussian distribution. Okay, So that one is one example of self-normalization, but here comes another example. And in this one, remember, we only assume that we have A and B arbitrarily dependent. And we are going to, they satisfy the canonical assumption. Again, the canonical assumption is here. So this is the canonical assumption. You have arbitrary variables, A and B square. They can be dependent as in whichever way you want. That has to be less than or equal than 1 for all lambda. Then you have the following exponential inequality. The probability of A over the square root of B squared plus EB squared bigger than X is less than or equal than the square root of 2 e to the minus X squared over 4. Don't mind the constants, because I'm presenting this inequality just as an illustration of the power of this technique. And the proof is relatively non-complicated. So now, this is sort of like, if I take the expected value of B squared here, this is an impossible inequality. That is to say, in general, probability of A over B cannot be bigger than X, cannot be sub-Gaussian. So this is, if you want to say, a meta inequality for sub-Gaussianity. As long as you have the control on the Laplace transform or the moment generating function of your variables, the canonical condition, you can get sub-Gaussianity. So in a later paper in 2009, we obtained the following. So under the assumptions of the canonical assumption, we can get that this is less than or equal than x to a power, to a negative power, times e to the minus x squared over 2. So really the tail of the variable that we obtain is almost Gaussian. So this is so by adding a term here, you get sub-Gaussianity. Now this is for any p and q bigger than or equal than 1, with 1 over p plus 1 over q is equal to 1. Now let's compare this with the normal distribution. Probability that c is bigger than x is less than or equal than 2 over square root of pi x to the minus 1 e to the minus x squared over 2. So you see the exponent, the decay rate is the same. But we are not making any assumptions about the dependence between A and B. Now, let me give you examples where this can be useful. So, for example, if you have standard Brownian motion and assume that t is a stopping time, then expected value of e to the wt minus lambda squared t over 2 is less than or equal than 1 for all lambda in R. So you can replace A by W and T squared by B and T by B squared. So you have that the inequality that we just showed applies when you take Brownian motion up to a stopping time divided by the square root of the stopping time minus its expected value square. That probability is sub-Gaussian. So here's a randomly stopped Gaussian process, and we can, there's dependence between the top and the bottom, and we can get sub-Gaussianity. The same thing happens with martingales. So you have continuous martingale. you take your martingale, MT, and then you divide by the quadratic variation plus its expected value, and you have sub-Gaussianity. This is for an arbitrary continuous martingale. Which satisfy the condition square interval martingale, arbitrary square interval martingale. Now, a very interesting result of Vercoux and Toti, I think, is the following. So you see, typically, you need to assume that you have like here we are subtracting by the quadratic variation, but when you have discrete processes, what Vercoux did was to show that the condition is satisfied by the sum of the i's with A and the sum of the di squared plus the conditional variance, okay? So these two, the sum of these two is B squared. So you can again go back and plug it in. Now, one important thing I want to point out is that you can use this type of inequality to test hypotheses. For example, if you have your variable B, okay, which is the sum of the squares or whatever, if you want to test whether or not the expected value of B is a given number, you plug in that number and you can calculate X to test that hypothesis, so that you get X so that this is less than or equal than alpha, and you can test the hypothesis whether or not the expected value of B is less than or equal than a number. So this can be used for tests of hypotheses in a very general context. Now, the next one is more modern. So as I said before, we don't like to make assumptions. So in this result, we have, suppose that you have a sequence of adapted variables, and we assume that the d sub i's are conditionally symmetric. So I'm dropping the moment assumptions. What I'm assuming is that the conditional distribution of di given the past is equal to the conditional distribution of minus di given the past. Under this assumption, no moment assumptions, then the e to the lambda summation of di minus lambda summation of the di squared over 2 is a super martingale, and this expectation is less than or equal than 1. Okay, so you could use this for stable variables, you could use this for Cauchy variables, and the condition is satisfied. So for stable variables, if they have a finite mean, then you have here, you put here if the variables have a finite mean, then you can get this inequality. And more generally, we can remove the assumption of conditional symmetry, and that comes by using decoupling. So note that any sequence of real random variables x sub I can be symmetrized to produce an exponential martingale by introducing random variables x sub I prime, such that the law of xn prime given x1 prime, xn minus 1, xn minus 1 prime, xn is the same as the law of xn given x1 up to xn minus 1. So you can construct this, and perhaps next time I will show you how to construct this sequence, so that then for the dn, the dn's are conditionally symmetric. So that means this if I have any sequence of variables xn and construct the tangent sequence which is what I call X prime. When I subtract, I have conditional symmetry, and this holds. Now, this result will be used to extend Kolmogorov's LIL to self-normalization without any moment assumptions. Any questions? Okay, so we have 20 minutes. Let me see what I have, what I can do. Okay, so that's the canonical assumption. Now, question is, how can you prove the inequality that I just presented? Now, there's a book by Berku et al. In a recent book on inequalities, where he applied self-normalized inequalities for all sorts of things. I'll give you the reference next time, where you can find an in-depth treatment of this type of inequality. Now, okay, so how do you prove such an inequality? What you do is, okay, so this is more like philosophy. So before I get into the actual proof, let us try to see what we want. So note that if one was to maximize lambda inside the expectation, so I want to come up with an inequality based on this fact. If I maximize lambda inside the expectation, as it can be done when A and B are non-random, taking the value lambda equal to A over B squared, we would get expected value of e to the A over B squared, 2B squared less than or equal than 1, and we would get the ideal inequality. But as I said, this is not possible. So how close can we get to it? And the technique is called pseudo-maximization. And it is basically using Fubini's theorem. The idea is you are going to multiply the left-hand side and the right-hand side by a density of indexed by lambda, so f of lambda, and then you will integrate on both sides. And since the right-hand side is just the integral over lambda, it will be bounded by 1. So on the left-hand side, you can pick any density to do this. And by using the Gaussian density, you can come up with the inequality that I showed you. So the idea is you multiply by the Gaussian density, and then you get the inequality that we were looking for. Are there any questions? Okay. I guess I'll leave a few minutes. We just have 6 minutes for people that might want to send me emails or questions. Next time, this presentation is already posted, but I think it's better if you read the slides before I go through the proof. The proof is a little bit intricate, so we're going to go through this, and we will also discuss boundary crossing and so on. So look at the lecture before next time. So I'm here ready to answer questions or comments. Now, I guess since nobody's asking questions, I just want to remark that this type of inequality is very popular in machine learning these days. The self-normalized LIL, law of literal logarithm, has been used to prove best possible algorithms in machine learning, as I will discuss later on. So there are tangible results in the theory of online bandits, classification of algorithms and other things. So I will post that paper as well.
Okay. Just I wanted to say that I sent the reference to this book by Bercu de Lyon and Rio. And in fact, I also wanted to mention that there was work by Abdou Touati, which was an old friend which died some years ago, and which was working on the same kind of inequalities. And his son, Touati, also is also working for applications of such self-normalized inequality for machine learning. So maybe there are some references to deal with.
I will post a survey that I wrote for the American Mathematical Society, which shows how this can be used in machine learning. Any questions? Any further questions?
Thank you. Can you hear me, by the way, or not?
I can hear you very well.
Okay. Okay, so I think that if there is no more questions, we all thank you, and let's go next week for the second part of your mini course. Thank you very much.
Okay, thank you very much. Thanks for the patience and attention.
Thank you.
Thank you.
Thank you.
Bye-bye.